Yep, okay. Welcome to the return of OpenStack Telemetry and the 10,000 instances. This is running in place of the telemetry project update. So I know out there it says telemetry project update, but we're going to be going over scalability testing of telemetry and some of the changes that have been made there. So scratch that. Let's change the name. 20,000 instances. Let's go for higher scalability. So introductions. I'm Alex Cross. I'm a senior performance engineer at Red Hat. I've been there for 4 years now. Been working on OpenStack for 2 years. Julien was also supposed to be here but couldn't make it. So let's talk about telemetry and scaling. We'll talk about why we scale test. We'll take a quick look at the telemetry architecture, the Nokey Architecture, the road to 10,000 instances, and then we'll go over some scale and performance test results and follow up or finish with a conclusion. So why scale test? We're going to determine the capacity and limits of our software. From that, we're going to try to develop some good defaults, some recommendations that we can, maybe hardware recommendations. We're also going to characterize the resource utilization and find out what bottleneck, what performance food group might we be bottlenecking on, if it's CPU, memory, network, or disk. Bottom line is telemetry has got to scale, because with OpenStack, we're talking larger and larger clouds, and there's only going to be more and more metrics we're collecting and more objects within the cloud. So the telemetry architecture hasn't changed much. As you can see, the OpenStack services are feeding data into the notification bus. You also have the polling agents grabbing data and feeding that into the notification bus. The Selamat notification agents pick that data up. It processes it through the pipeline, and then it'll publish event data to Panko. It'll also publish metric data to Nokey. From there, you have AODH, which is evaluating alarms. And that queries the Nokey metric API there. So the Nokey architecture. There's two main components to Nokey, and that is your API daemons and your metric D daemons. So for Nokey version 4, there's actually no longer, there used to be a scheduler daemon, and that was in 3.1 and 3.0. It's no longer there for 4. They've moved to a consistent hashing, and there's no longer a need for a scheduler process. There is still the coordinator. The coordinator is hosted in Redis, and that allows locking of metrics for processing. And then on the storage side, we have 3 separate areas that you can configure for storage of data. In the previous versions, the measure storage and the aggregate storage was actually the same storage driver. So it would be implemented in there, but if you pick Ceph storage, you could only use Ceph storage for measure storage or aggregate storage. So for Nokey 4, that has been separated so that measure storage is now separate from your aggregate storage. So a good example of this would be using Redis to store your incoming measure data and having Ceph store the long-term aggregate storage, aggregated processed metrics. And then lastly, there's an index there, and that's in MariaDB. All right, let's move on. So the road to 10,000 instances. With Okata, with the setup that we've been kind of using as our performance baseline, we had a really tough time getting above 5,000 instances, especially after tuning for parameters and trying to reduce the workload as much as possible. And that resulted in some bugs and some changes into Nokey 4. And our goal there was to get to 10,000 instances with less tuning and an even more difficult workload. And then, of course, for extra credit, we'd like to go above. So for workloads, I've used booting instances with a network, and I've done that 500 at a time, and then have a quiesce period. That way I could see whether or not the backlog was growing infinitely, or if Nokey itself was handling the amount of work. We've also eliminated the use of having a network in that case as well, so we don't have to have interactions with Neutron in case we have other scalability issues there, or maybe that particular daemon is not deployed in its most performant fashion, then we can kind of limit the test a little bit more and just do instances. And in that case, we booted 1,000 at a time and was looking at the stepped graph there. Of course, that's just kind of the workload that we put on the back-end system. We also want to stress the front end and see how well can we create metrics and delete metrics, how speedy is creating and deleting resources, and then of course you want to get the data too, because it's one thing just to store it, but if we're not getting it, then it's kind of pointless. Here's the hardware that we've used. It actually hasn't changed since the Okada cycle. The only real difference here is that I had a whole lot more compute nodes. The only other thing that's not listed there is there was 10 gig networking. So this is the topology of the actual test hardware. The undercloud machine, that's just simply a machine that deploys and creates our overcloud. And in our case, it also hosts my framework that does the testing. And you can see there that we used VLANs to separate the various networks, internal API, storage management, tenant, and an external network. There's also a provision network as well. That's not on a VLAN. So the first test I'm going to run through this data here is 10,000 instances with NICs. The settings that I had for Nokey, the only real, just a couple small changes there, just added a few additional metric D workers. The deployment framework itself deployed 12. I bumped that to 18. Same thing with the API workers. There was 12. I bumped that to 24. And that's per controller, so there was 3 controller nodes. So 3 times each of those numbers, the total number of actual daemons that were running inside this test. On the Selamat side, actually bumped the notification workers. Also tuned the rabbit prefetch. One of the reasons you want to do that is you don't want Selamat to grab the entire chunk of messages out of the message bus and shoot through the roof in your memory and basically cause your cluster to fall over if you're at a high enough scalability. The polling interval was the default, which is 300 seconds. That does match the archival policy within Nokey itself. And that's another large improvement over, well, not necessarily improvement, but this is a difference in the testing from Okada, where in Okada we tuned the polling interval out more to try to even get a higher scalability. So this is the test results showing the backlog along with the instances itself. So I realize that it probably shows a little bit small up there, but the slides will be available afterwards. And you can see the blue line is actually the instance count, and that's going in a stepped process of about 500 instances each time. And the yellow and green lines is the actual backlog within Nokey itself. So the yellow is the number of metrics that have measures that are unprocessed, and the measures themselves is the green line. So you could have a metric that has more than one measure that hasn't been processed. And you start to see that occur at higher scalabilities, where you may have a metric that has a few measures backlogged before it gets processed. In this case, we can see that after around 5,000 or so instances, we start no longer seeing this return to 0 behavior, where you're seeing the yellow line no longer touch the bottom. And if you look, that is on the opposite side. That is the backlog. It's on the y-axis, the right side y-axis. And even though we no longer touch 0 at the higher scalabilities, there's only a slight delay between when that metric is processed and what data you're seeing. So if you ask for, I want the average CPU utilization up until 12 o'clock, it might only have till 11:50. But if you pass an actual flag to the API, -- refresh, it will force it to process that data that's off the backlog itself. So you can get the latest data that's off the backlog there. This is what the CPU utilization looked like in this cluster, and this is across the 3 controllers. So to avoid having way too many slides, I didn't include all the other nodes. This is the memory utilization. And what I did here is to try to highlight I aggregated each particular node type. So the top is the controllers. So that's all 3 controllers. That's the memory summed up all on top of each other, so stacked. So you can see that we still had plenty of memory available on those controllers. And then if you look at the Ceph storage nodes right below that, plenty of memory there. And finally, the compute nodes at the bottom, plenty of memory there. Here's the disk IO utilization on the controllers. So really what you're seeing there is logging and IO for the database. And then this is the disks on the Ceph storage. So definitely a lot more utilization for the number of OSDs that we have. And part of that is just the number of IOPS that we've created with this test. There is NVMe storage on the Ceph nodes themselves. So the OSDs, their journal is hosted on the NVMe, but that's it on the NVMe. So the high utilization is mainly due to the fact that these are spinning disks. So let's go on to the next test. 20,000 instances we got to. And this one, we did 1,000 instances booted. We didn't do it with the NICs. If you did notice on that previous graph, each step, the step kind of got elongated. And what was happening there is the interaction to create the NIC on the actual compute node started to slow down. So we were running into an issue actually with Neutron just on booting the number of instances within that test bed. That's a different issue that we're still working on. So for this workload, we just didn't include the NICs. We don't have that problem. The graph looks a lot sharper. And we did do front-end API tests as well. So we had 5,000 get measures, 1,000 metric and resource create deletes. And then you can see what we did for tuning here. We did a little bit. We bumped the number of metric D workers to 36 and the notification workers to 5 on each of those controllers. So this is what Okata looked like. So you probably remember that, me presenting this back in Boston. Wasn't too happy with that. Well, this is not Pike. Here's Pike. So we got to 20,000 instances, and you can see that we were actually able to keep the backlog down well into the 13K range, where it was returning to 0. And that's at a 300-second polling interval. Whereas with Okata, we were running with a 1,200-second polling interval. So that's 4 times greater granularity you're getting in your data, and we're actually able to do a lot higher instance count there. So this is a huge improvement. And you can see here that by not including the NICs, we have that very sharp growth every time I grow 1,000 instances. And this is what the CPU looked like. CPUs look like across the controllers. You can see we're getting up there. There's still some idle CPU, but these are hyper-threaded machines, so it's not exactly, once you kind of pass the core count, you may not have that same efficiency in CPU. Here's the memory. You can still see we have plenty of memory on almost all the nodes. The compute nodes, we got a lot higher. And here's the disk utilization on those controllers. You can see the spikes corresponding typically hourly, and then there's also some spikes with the booting of the instances itself. And here is the disk utilization on the Ceph storage nodes. The other thing I wanted to mention, I don't think I mentioned before, was that obviously I couldn't put a slide up here with 12 Ceph storage nodes. So this is just the first 3 of them. And then if you were to graph that with all the 16 OSDs on each of them, you'll obviously it's like 192 utilization lines. And then add the NVMEs after that too. So also wanted to point out that the network was not a bottleneck here. So we can see that on the this is EM1 interfaces on the controllers. This was hosting the storage and storage management networks. There was not a network bottleneck there. And EM2, which is doing the internal API and the tenant network, could also see that there is not a bottleneck. So let's look at some of the data from the actual front-end tests. So this is from the 20K test, and this is getting the measures. And You could see we have a baseline at 0. Really, there's very few actual resources for me to grab measures off of, so more than likely that was all cached and very fast. But even after I boot 1,000 instances, you can see very little difference in the performance there. And then I wanted to point out that this is the minimum, median, 90th and 95th percentile. So the green line is the 95th percentile. It's probably the one you want to look at the most here. I didn't graph the max because there is spikes in the max, and then that throws off your axes very high up there. You can see that probably, or roughly around 10,000 instances, we saw roughly a doubling in the response time at that point at the 95th percentile for getting your measures. So obviously there probably could be some work to be done here to probably smooth this out. We want to make, obviously flatter would be a lot better. We want a flat line, a very low line, of course, not a flat high line. So creating and deleting metrics. And so here's the graphs on those. And you can see that they're relatively flat as well. There's some spikes towards the end there. And deleting is much faster. Same thing with resources. There was some spiking there at the end. So for tuning, for NoKey, for Pike, the big thing is you're just going to have to kind of tune the number of metric D workers and your API workers you need. I would recommend for the incoming storage that you use Redis. That's what we used in all that testing there. In Okada, because we could not split the measure storage from the aggregate storage, and we used Ceph, there was an issue in the driver back then where we would use a single OMAP object that would store all the keys, and each key mapped to a actual 16-byte object within Ceph, and that caused an enormous problem inside of Ceph. So my recommendation is to switch to Redis. It also is actually split up such that now that we have the consistent hashing, you have a number of sacks that the actual incoming measures get divided into and split amongst the metric D daemons themselves. So even if you were to actually use the Ceph storage incoming driver, you should not encounter nearly as much of a problem, or it should be at a much higher scale. For Okada and Newton, you want to tune your metric D and API workers as well. And you also have some fine tuning between your tasks per worker and your metric processing delay there. And the last thing I want to mention is you want to avoid the scheduler. You want to make sure you're using the latest version of NoKey, because there was a starving condition where if you did not process your measures down to 0, you could have those last few metrics continuously grow measures. And if that grew unbounded and you weren't monitoring your network, that's where you'd have that problem with inside of Ceph or some of your other storage backends. So for Selamat, you want to avoid overwhelming the NoKey backlog if you can. Basically what that means is collect what you need and what you're going to use. If you collect the world and you're throwing away most of it, that's kind of a waste of work. So the best performance gains are not actually doing the work you don't have to do. So just remember that. You want to check that you have that prefetch set, and you also want to monitor RabbitMQ as well. So for Pike, it's really a matter of tuning your agent notification workers. For Okada, you probably want to disable the collector because you can publish via the agent notifier in Okada. And Newton, you're kind of stuck with the collector, unfortunately. So conclusion, OpenStack Telemetry is now proven at least to the 10,000 instance mark or more in Pike. There's minimal degradation in the response timing of the API as more and more metrics are collected. You can see it was pretty flat there. With that being said, though, of course, there's always room for improvement. So some things that we could work on, reducing the load on the archival storage. You can see that I pointed out about the Ceph storage nodes. There was very high disk utilization, and that was just your control plane telemetry using it. So one thing that I would have liked to have done with this testbed had I had the time was carve out that NVMe, some space out of that partition of the NVMe, and host an actual metrics pool off of that rather than the spinning media, because you don't want that affecting your actual, maybe your Cinder volumes or other things utilizing that Ceph backend. We also want to work on the spikes in the API timing. You can still see that although it was pretty flat, there was still some spikes and some degradation in the API. The big issue there is really that the front-end API is sharing the same pipe as the back-end. So you're competing with the new measures being thrown into the backlog when you're asking for that data there. So if we could separate that, obviously then it becomes an issue of how many requests I want to be able to throw and how many workers do I need, how much resourcing do I have. And then, of course, more performance testing with more storage drivers. And that's all I have. And if there's any questions, I'll take them right now. I think we're pretty much close to out of time, though. Yeah.
I suppose that Ceph is the fastest backend that you have. Like, it's the one you listed because it's the fastest. I suppose Swift will be slower by getting.
Yeah, so I have some experience with using Swift. So the question was is Ceph the fastest backend? Ceph is the most tested backend that I have. As far as being the fastest, I would say it is the fastest, although it's difficult to create an equal test between Ceph and Swift. Often because Swift has a whole number of workers itself, or processes and daemons as well, such as the proxy worker. You have object, account, container servers, replicators. So you have a whole number of additional daemons itself, and you need to plan for those as well. So in my previous testing that I've done similar to this, you also have to construct the Swift ring to utilize that, like the NVMe storage and stuff. So, but what I've seen from the same test is that I've been able to get a higher scalability with Ceph on that same hardware. Another question.
Related to the development of Selamat. Because in the Selamat official documentation, it's not recommended to use a poster, right? It's recommended to use a notification mechanism to collect metrics. So does it still make sense if we want to add more poster in Selamat?
That would not be the best question for me. I don't have a good answer. The question was, is it recommended to use a pollster over publishing directly to the notification bus, so the notification agent would pick up that data? I would leave that to more of the Selamat devs there. So, any other questions? Nope. Thanks, guys.